Okay, so I would like to first thank Alain for the wonderful presentation of what I will present you now. I will try to make it short, but it's the idea of, I did a presentation a few days ago with an introduction to cuprate superconductors. So I did a presentation a few days ago about cuprate superconductors. And here it will be more detailed of what we did with this idea of fractionalized perient density wave. It was indeed extremely inspired by the data Alain just presented on Raman scattering. This was one of the main inspirations for this idea. So I don't go over the diagram. First, I don't have time, and you heard that already in a previous talk. I will present just the idea of fractionalization. So when you fractionalize an electron, as here, you cut it into a charge holon and spin-on, and this is operator or field space. And in order to control the number of states on site, you impose a constraint which says that the number of spin-ons and holons is equal to 1 at every site. And this is accompanied by an emergent gauge field, so a gauge transformation with a fictitious U1 gauge field here. And the system, you can see if you put the gauge field, is invariant with this transformation. So we decide to do the same, but for a boson. And a boson which is fragile, which is a perient density wave boson. So here it's in terms of operator. Here is a perient density wave. Write it as a commutator of charge modulation and a boson corresponding to pairing, so particle-particle and particle-hole modulated pairing. So now we have a constraint again between the two fields, and the perient density wave fractionalized into a charge 2 bosons and an operator here, particle-hole, which breaks translational symmetry. Again, you have a U1 gauge theory, a gauge field, which is emergent here. And our ansatz is a pseudo gap is an entangled state of the two with a constraint. So the two orders we know are in competition. So it is our way to put them in competition, not by Gibbs-Borlado, but by entanglement. And it requires an emergence of a gauge field at T star, which is not such a simple structure if nature decides to do that. So we wanted to test this idea on experiments. So this is a slide. So the system below T star is described by an effective field theory, which is a chiral rotor, a quantum rotor model. So it's a chiral model, which is equivalent when you do a Hopf mapping to a CP1. So it will be equivalent to a nonlinear sigma model with a gauge field. And we have some predictions already of what's going on here. So you have incoherent bosons at plenty of them in this region, some emerging gauge field at T star, and at TC, importantly, all the phases are frozen. So this is very non-trivial if you do that, because the phase of the charge order parameter is frozen with the phase of the superconducting order parameter. Well done. This very nice conference, and not to end up in a state of frustration as I was 1 hour ago. So it's where I was. So it's a phase diagram. Oh, okay. This is a conversion to PowerPoint. So this beautiful thing is a chiral rotor model. It's not what it should look like, but it's okay. We'll do with that. So it's equivalent to a CP1 model, and the important thing is with this idea of entanglement of charge and spin density, of charge and density wave and superconductivity, you have some chiral model which describing effectively the physics here for those which are field theoretical. And so I have a gauge imaging field here, freezing of all the phase at TC and incoherent boson there. And this has tremendous implications. So first here is the experiment by a group of Seamus-Davis. Here is the charge distribution you see at a finite temperature at B equals 0. And look at the phase slip over there. The distribution of the phase slip is completely random. Now they put 8 Tesla and subtract, and you see the vortex core. And now the distribution of the phase slip inside the vortex core is centered around 0. So it's a completely different distribution from here to there. So it's very difficult to understand because basically the coherence of the phase slip of the charge modulation is 1 order of magnitude bigger, the coherence length, than the coherence and the amplitude of the charge modulation. It is very, very unusual. So within our model, we can explain it by the fact that below TC, it's where they are, the two orders in competitions, they lock their phases. Basically, it means that the charge density wave behaves like a pair density wave. I agree it's a bit unusual, but I think if cuprates were so usual, we would have solved them. So this as a link, okay, this is a great transparency again. Just to say that with late Konstantin Yefetov, we had work on an idea also where charge and superconductivity are entangled, which this time required an emergent symmetry, not gauge field, but the constraint is the same. And again, it's described by a chiral model below T star. So the two models, it's just different way to get entanglement of charge and particle and particle hole pairs. So I come to the predictions. I will try to go quickly. So we did a bit of RPS. Sorry for equations, guys, but okay, I'll pass that. So we have a model I will describe with word, which is a TGV model, and we put the strong coupling in a mean field, so it's very kind of lousy with Gutzwiller, and we calculate the particle hole sector and split them a little bit with second nearest neighbor here. So basically what we have as minimal ingredient is the two orders. They have roughly the same order of magnitude, and charge order is a little bit bigger than superconductivity. This is a very minimal model that we could make in order to have a good mean field. And with that, to come to the experiment that James showed you for RPS on bismuth 2212, we can explain it pretty well. Like the constraint is opening the pseudo gap, but the pseudo gap has some structure in Q space, so the KF wave vector are differentiated, and you have the backbending. So it's one good thing. It's because of the particle that we get the backbending. So we also compared with the DMFT and the hidden fermion that Professor Imada presented at the last session. And so he claims it doesn't agree, but it's our interpretation that with charge density wave, we could identify charge density wave with a hidden fermion. Raman scattering by experiment presented by Alain this morning, we get it naturally. As I said, it was something which was very influential for our work. Just because in order to get this type of emergent gauge field or entanglement, you need to have the two orders at the same order of magnitude, the two gaps, not the two orders, sorry, the two gaps at the same order of magnitude. That's a requirement. So we believe it's important. Also, the charge order gap follows T star and not the charge order temperature, which is something very unique in their experiment. But you see it only below TC, not below TCO, which is something incredible. I mean, why should softening show up below the superconducting temperature? I mean, if it's just two orders in competition, like in niobium diselenite, softening should show up below TCO. And we explain here this with our model by saying that the phase of the two orders lock below TC, but above TC they fluctuate too much and they wash out the softening. I tell you ideas like in one. And then I would like to just say it's maybe the most important. We get some kind of ideas on the strange metal. Again, for people here, the strange metal conundrum was the following. So it's here. It's maybe one of the biggest mystery of cuprates for 30 years. You have linear resistivity for many decades of energy, and when you destroy by irradiation, you see linear resistivity to t equals 0, which is very difficult to get with any model. Moreover, one doesn't see it here, but believe me, it's a quasi-Drude-like. So we know on top of it that if you look at optical conductivity, this linear resistivity is proportional to the Drude width, to the lifetime inferred from the Drude experiment. At the other time, and this was pointed out by Phil Anderson in a very seminal paper, the cotangent hole has a lifetime goes like t square. So if you just do a simple electron model or free carriers model for that, here you have you extract a lifetime which is inversely proportional to t, and here inversely proportional to 2t squared. So you have two lifetimes. So the way we try to deal with that is tough problem. Here again, another type of experiment, but it goes quick because James mentioned them. This is an experiment by the group of Nigel Hussey in Bristol, and they interpret it, that's discussion with them, as if you have another type of carrier which is present in this region. They have a new component that they claim is isotropic in the magnetic field, is incoherent, meaning doesn't participate to the thermal Hall conductivity, and is participating to this Planckian limit or linear anti-resistivity. So in our model we have incoherent bosons, and one reason also we could get incoherent boson is this wonderful Mills experiment by Mitrano et al. So it's in the strange metal, strange metal here. And you see something incredible. I mean, the compressibility, you see as a function of frequency. See this plateau? The energy of this plateau is roughly close to 1 electron volt. It's huge. It's an elephant in the room. So what could cause a plateau at 1 electron volt in this compound? One idea came from people doing statistical physics, actually in my lab, working with actually Parisi, and they told me, oh, but this is the jamming transition. Namely, if we believe them, I don't know, to get the jamming transition, you need to have bosons which interact with each other, and then they jam. Now, why not? We could say that. So we checked in our model, we have bosons which appear at high energy, and they are charged to a finite Q and coupled to the lattice, so they could participate to transport. So we did a first calculation on that with those bosons. We didn't find literature any calculation at all, so it's the first one. And we found something very nice. In 2D, they go in linear in temperature for resistivity with quasi-Drude-like optical conductivity. And since they are extremely incoherent, they have a Landau damping. You don't see it here. They don't participate to Hall transport. So then the picture would be that they could short circuit maybe the transport in X direction, longitudinal transport, and then Fermi electrons and Fermi C could be responsible for the T-square in the Hall transport. Okay, we also have a prediction, now I pass, in terms of Josephson junction of this very unusual ID, and in particular new Shapiro steps are showing up. So with this, I will thank you for your attention, and thanks to let me present these results.
Okay, thank you, Catherine.
Well, I have two questions, but maybe we're short of time, but we'll talk about a little bit more about the Shapiro steps. I didn't quite, it was too fast. What is unusual there? Can you explain?
Yeah. So in this work, we try to compare a situation where the two orders compete, and the situation of this fractional sphere density wave where the two orders compete, but the phase lock. So basically, you induce an effective pair density wave. I mean, the charge order, see the phase lock, basically in terms of symmetries, your charge order behaves like a pair density wave. And this, when you do a Josephson junction, will induce some tunneling, extra tunneling from the pair density wave sector to the other pair density wave sector. And this produces some observable. So you have extra Shapiro tape, and you have also modulations. If you're able to slide one part compared to the other, you should see modulation at the wave vector of the charge density wave, not half of it. So, I mean, we try to get now some direct experiment, because, I mean, indirect, it was nice, it was very inspirational, but the idea is unusual. I mean, it's an entanglement idea. I mean, around if you talk to Jansanen or Subir Sachdev, they will tell you that the QCP is the most entangled QCP in the world, and that everything is entangled. So we do something a bit less, bold, but still. So to me, the less bold thing possible is try to entangle the two orders which have been seen, with its charge and superconductivity. It's just what we are trying to do.